Okay, so I think we should get started, right? Uh, so hi, I am Bismay, and for today's reading group session, I'll be presenting a paper. The paper in question here is Deep Learning for Symbolic Mathematics. This paper was published last year around I think November or December. The authors of this paper are Gulam Lampel and Francois Carton. Both of them are researchers at Facebook AI. Before starting this, before starting the presentation, I would just like to say that I'm not really proud of my mathematical aptitude. So uh, parts of the paper that relate more to equations or derivations, I have kind of skipped off over them. I will be mentioning the formulas wherever necessary, but for most part, I will just breeze through them. And if you want to look into them in more, like if you want to look into them in a more detailed way, you can check out the paper. I'll share the link after the presentation. Everything that needs derivation or explanation is mentioned in their appendix. So with that, I would like to get started. First of all, I would like to give an introduction of the problem statement that is involved here. So because in this particular paper, the what's interesting is not the kind of novel technique that they are using to solve this problem. They are not really using anything new or sophisticated to solve this symbolic reasoning problem. Instead, they are just using standard sequence to sequence model. What's interesting is the problem statement, right? So what happens is that neural networks are used to capture statistical information, and we know that statistical learning is very different from rule-based inferences. So when neural networks makes a decision that a particular image belongs to a category, it bases it on the different uh, pixel values it was able to see in that particular image, and uh, how these different pixel values mapped in other images, and the what kind of labels they had, right? So they don't really, the neural network doesn't really look at an image and sees a person and says, yeah, there is a person. So it will just look at the whole image, and it will find some kind of mapping that will help it to capture what is going on there. But historically, neural networks have also performed very poorly when it comes to symbolic reasoning tasks. There have been a few studies that were done in this particular domain. I think there are a few papers that were published in the last 5 years or so, where they tried to get neural networks to do simple arithmetic tasks like multiplication or addition, but the results were very poor. There were either the results were very poor, or some kind of components was introduced into those neural networks that made them biased toward the particular problem. But the problem that the authors pose here is that they try to solve integration and differential. They try to calculate integration and solve differential equations. Now, from a initial viewpoint, you would think that these problems are something of a symbolic nature, right? Because humans are usually taught a set of rules that we need to follow to solve integration, or to calculate integration or solve differential equation. Like both of these problems are kind of similar, because to solve differential equations, we mostly apply integrations. Uh, and for in case of machines, for frameworks like MATLAB and Mathematica, They use very complex algorithms that span multiple number of specific cases, and they are very long and uh, are still they still generate many incorrect results. Given that this is a problem of rule-based inference, how do we solve it using neural networks? Now, the authors argue that the given problem is a simple case of pattern recognition, since to solve a particular to calculate the integral for a particular expression, what we need to do is just find some kind of patterns in that problem and replace it with another pattern, right? And this particular framing of the problem makes it sound more like a sequence to sequence problem that is used in translation, machine translation. So when we translate some kind of language to look a particular sentence from one language to another language, or create a answer for questions, the machine is generally just seeing what kind of pattern is there in the source sequence, and just generating some kind of sequence that is should be valid for the provided sequence, right? So we use neural networks or in particular sequence to sequence model in this case to help the model learn these common expressions and be able to give us the correct solutions for the integrations and differential equations. Uh, for training the model, we would need a large data set, like neural networks usually require large data sets. So the authors come up with various techniques to generate these examples where they were able to obtain pairs of problems and solutions to train the sequence to sequence model. To start off with, we would need to be able to present mathematical expressions in more of a natural language format, because since we are using neural networks that are used to translate natural language, or that are used to encode and decode natural language, the provided sequences should be in similar format as well. So to do this, what the authors did was they first converted these mathematical expression to trees, right? So expression trees, I think most of you should know about it, that they are used to denote how a particular mathematical expression should look like. So the internal nodes, you can see here that the internal nodes represent a particular function, right? So the addition and multiplication is a binary operation. So it spans over usually over two variables or to one constant and another subtree, or another variable or another subtree, something like that. And a unary operator like the sine function is used to uh, just has one child node. So here you can see in the third plot that only x is the child node for sine function, since it only takes in one constant or variable as an argument. So first we convert mathematical expressions to these kind of trees. Now these kind of trees help us to generate different kind of notations easily, and as well as store them for future use without having to store them in a more unconventional string format, right? After converting them to expression trees, what we do is we convert them to a prefix notation. I do know, if you know what a prefix notation is, it is simply if there are two terms that need to be added, for example, x plus 2, it will be written as plus x2. by using prefix notation, we are able to eliminate the need for use of brackets. So since there are no more brackets necessary, the expressions are smaller than what should be required in a standard infix notation. So to convert mathematical expressions to natural languages, we can just say that the standard expressions are converted into their corresponding prefix notations. Uh, After we uh, this is how we'll be presenting the data to our model, right? Prefix notation will be how we'll present the data to our model. But first of all, we need to generate that particular sequence of mathematical expression, and to do that, we could use some kind of naive algorithms like recursive techniques, or algorithm where we'll just randomly assign probabilities to the nodes of a particular tree, and then we'll decide whether that particular node is a leaf node or a binary operator or a unary operator, something like that. But the researchers found that these kinds of techniques tend to favor deep trees over broad trees, right? So in the first plot, you can see it is a kind of a deep tree. So there are multiple levels in that particular tree, and it goes deeper into as we proceed. But the second plot is something more of a broad nature, where there are levels of the trees, but their branches extend to both left and right. So they found that these naive algorithms also favored left-leaning trees over right-leaning trees. So the third kind of tree would be favored over the fourth kind of tree. And so I mean, if this kind of favoring was noticed, then the author decided that it is best not to use this algorithm, since they wanted problem space, a sample set that is more representative of the problem space, right? So now the problem space wouldn't really be consisting of only deep trees or left leaning trees. It should equally consist of all of these kinds of trees. So and they created an algorithm that generates all of these kinds of trees with similar probabilities. Now if you want to look up this algorithm, you can check it up in the appendix section of the paper. It is kind of it spans around 2 pages or so. So I decided not to discuss it, because it does not affect how the result was obtained. So yeah, if you want to look it up, you can just go, and I think it was present in section C of the appendix for the paper. Number of expressions. Our problem space would consist of a tree with n internal nodes. There will be P1 unary operators. So unary operators are operators like cos, sine, and exponential and logarithmic function, which will just take one variable or constant as an input. And there is a set of P2 binary operators, which are addition, multiplication, subtraction, etc., where they usually take two inputs and generate one output. And then there are a set of leaf nodes consisting of variables, constants, and integers. So I mean, these are the terms that will be used to generate the expression, right? These expressions what will be then used to create the problem solution pair for integrations and differentiation. So these expressions should be representative of the problem space that we are looking into. They should not really be just very this should not really be a very small part of the problem space, very concentrated part, but we need them to be homogeneous. They need to be spread out, and uh, yeah, so like our model should be able to obtain results for them. So to give a idea of the number of possible expressions that we can generate using the given set of parameters like n internal nodes, p1 unary operators, p2 binary operators, uh, the authors came up with these formulas that will help us calculate what kind of the number of expression that we'll be able to generate. For example, here the first formula denotes the number of binary trees that we will obtain with n internal nodes. The second formula is what we call Schroeder number, which calculates the number of unary binary trees with n internal nodes. So it, as you can see, it contains some terms that like work with recursion. So you'll have to use recursion to calculate these values, and using the second term, the authors were able to uh, find the final formula, which calculates the number of possible expressions given n internal nodes, p1 unary operators and p2 binary operator. So now you can see that in the second expression, we calculate the number of possible unary binary trees. Now, since we are calculating only the number of possible trees, and it has no relation to what kind of operators it has, so the set of operators used is just like one. So there is one kind of operator, unary operator, and one kind of binary operator, so that the number of expressions don't increase, right? Because to calculate the number of trees, the internal nodes should be similar to each other. Uh, and here the terms are replaced with the number of unary operators, number of binary operators, and leaf nodes. If you just replace p1, p2, and L with 1, you will be able to obtain the second formula from here. So like these are pretty much the same formula, but the values have been substituted to solve for the number of possible expression with n internal nodes and p1 and p2 binary unary operators. This graph shows how the how many number of expressions will be able to generate given a particular set of parameters. So the last two curves actually denote the number of possible unary binary trees and binary trees. So you can see here the value of L equals to 1, P equals to 1, and P2 equals to 1. Sorry, P1 equals to 0 and P2 equals to 1. So this refers to the number of possible binary trees. And I mean, even in with 28 internal nodes, the number of possible binary trees is about 10 to the power 18. And if we just include unary binary trees, it really doesn't increase that much with respect to what was before. So it is basically somewhat more than, like, I guess at 28 nodes it is around 10 to the power 4, I guess 16 or 15, something like that, and this is about 10 to the power 18 expressions. And as we increase the number of leaf nodes, you can see the number of possible expression increases dramatically, like from 10 to the power 18 to about 10 to the power 40, 45. Yeah, so about 10 to the power 45 when we increase just the amount of possible leaf nodes to 11. We are not increasing the value of p2, we are not even putting in any value of p1. So without any kind of unary operator, it is able to create this many expressions. So it would be fair to say that with this kind of problem space, we should be able to obtain a large amount of data that can be used to train our model. So to create the data set, now we looked at the statistics. So what kind of what the problem space looks like, how many possible expressions there are. So now to create the data, we cannot randomly sample these expression, right? Because many of these for many of these expressions the solutions really don't exist. uh, so we would need to find a way to separate the expressions for which we can easily find a solution, because without that we'll be unable to train our model. uh, the mathematical problems that are addressed in this paper are function integration and solving ordinary differential equations of first and second order. So we'll first look at how the data set was generated for integration, and then we'll look at how the data set for ordinary differential equations was obtained. To generate data set for integration, there are three different methods that have been used. So the first and most straightforward method was forward generation. We will take a mathematical framework that is able to calculate integrals for a given expression. So here the authors have used SymPy. It is, I think, a Python-based mathematical framework calculates, which can calculate the integral given an expression. So what they do is they first randomly generate expression, check if the expression is valid or not, like if the solution for it may exist or may not exist. Like most of the time they just pass it on to the mathematical framework, and if they are unable to obtain the solution they discard the expression. If they get a solution, they have a like problem and solution pair, right? So they add that example to the training set. So this method, although it works, it very slow and dependent upon the mathematical framework. So without so we can't really compare the results of our own model with the mathematical framework, since we are using it to generate the data. So the mathematical framework should have almost 100% accuracy in this case. uh, and also calculating integrals is kind of slow, and since we need a large amount of data, we can't really depend on this method for creating most of our data set. To overcome the problem, what we do is we do something called backward generation. This is a much simpler idea. So in the previous method, what we did was we calculated the integral of a randomly generated expression, right? So we calculated the solution from the problem. But if we calculate the derivative of a randomly generated problem, we are able to find the problem from the solution. So we start up with the solution and find what the corresponding problem for that particular solution is. So yeah, we first start with a random expression like in the previous step, and we calculate the derivative of the expression, and then it is added to the training set. It is very fast, like much faster than forward generation, and it really doesn't depend on any kind of mathematical framework, and hence it is like gives us a better representative like a subset of our problem space. Now there is another method that was used to generate the data set for integration. What happens in the previous backward generation method is that uh, the probability of randomly generating a long sequence is like really low. So when the random expression generator of the authors generates these expressions, they tend to be simpler than what is needed to be. And what happens is that when we calculate derivative of these simpler expressions, the derivatives are longer. So the problems are always longer than the solution in the case of backward generation, since we are starting with a very simple expression, and when we calculate the derivative, it tends to be somewhat longer, hence the problem is always longer. Most of the time the problem tends to be longer than the solution. To overcome this, to address this, the authors came up with another technique where they start off with multiple random expressions. In this case, here they started off with two random expressions, f and g. So this would eliminate the issue that the solution was short, since we are starting off with multiple expressions. So the solution will always tend to be longer. And after that, what we do is we'll calculate the derivative with respect to fg, and again integrate over it. So we'll be able to obtain a term something similar to this, right? So fg equals to integration over derivative of f multiplied by g plus integration over f multiplied by derivative of g. To obtain the terms, the solution for these particular functions. So what happens? We have a particular problems space here, I guess. I mean, this would be the okay. So let me see. Fg equals to gf of g. Okay, sorry, I'm kind of blanking out right now. So what happens is that the authors would look up if any of these two terms are present in the training set, right? So they will see if any of these two terms are present in the training set, then they will be able to infer the other term, since they already have the value of fg and one of these terms. So that way they are able to like calculate again what the problem will be from the solution. And if they are able to find one of these terms in the training set, then they add it to the examples. Otherwise they discard it and like start off with a new expression, like a new generated expression. So I think that's it for ordinary like integrations. After that, we have ordinary differential equations and of first order and second order. So to generate the data set for these two kinds of problem is fairly simple. We know that the solution for these problems are usually functions. So what we do is we generate a function that that will be the solution for that that will be the solution for the problem, and will like the random function should be a function of x and c. So a constant for which the function should be solvable. To make sure that the function is solvable in c, the authors limit the occurrence of c to one leaf. So in the whole expression, the c only occurs at one place only, since all the functions and operators that are used to generate random functions are invertible, will be easily able to solve the problem with in C. So after that, we'll obtain a term that is similar to what is written here, f of x, fx, and after we can then differentiate with it with respect to C and simplify it to obtain our first order differential equation. Now to generate the second order differential equation, like you should know, like the random function that was generated at the start was the solution, and the one that was obtained at the end, the expression that was obtained at the equation that was obtained at the end is the problem. So we start up with the solution and create the problem. Similarly, to create second order differential equations, we first generate a random function with two variables, c1 and c2. Sorry, two constants, c1 and c2, and one variable. And this function should also be solvable with c2. But we cannot make it so that it is solvable with c1. So the authors just restrict it to be solvable in c2, and after we solve it with respect to c2, we'll differentiate it with respect in x, and then solve it in c1, then again differentiate it. So there is the double differentiation here. there is double differentiation here, which leads to the creation of second order differential equations. Now we know that solve the function being able to be solved in the C2 or C1 is very important. So we can't since we can't make sure that the function is always solvable in C1, what we do is we'll just see if we are able to solve it. If not, we'll just discard it. That's it. So but for 50% of the problems they were able to solve it in C1, and hence they obtained a pretty much good amount of data for second order differential equations. After that, there was some data set cleaning stuff. You know, equations were simplified. So for example, if there is a equation like x plus 1 plus 1 plus 1 plus some kind of repeated term, they will just combine it and merge it all together to give it a more of a simplified view, like x plus 3 or x plus 5. They will, so, and also they do this to reduce the number of unique possible sequences, since if we keep the sequences to as minimum length as possible, then they will tend to be similar to each other. If they are similar to each other, they will be equal to each other, else there will be unique expressions everywhere. There is also a coefficient simplification where we'll just merge together variables of different expressions uh, with equivalent expressions up to a change in variable. For example, in a particular expression with x plus log x, x plus x square plus 2x. So here their expressions with similar variables are x plus 2x, and there is a term with x square. So they will just merge together x plus 2x to form c of x. So yeah, so this is coefficient simplification. You can look this stuff up in the paper. It is quite simple. So I'm not really discussing it in detail here. And there are also some invalid expressions that need to be removed. So there are expressions for which there were no solutions that could be obtained and other stuff. So they were simply removed from the data set. After going through the steps that I previously described, this is the kind of data set we are able to generate. This is so you can see, as I said before, that in backward generation, the length of the input tends to be longer than the length of output. We start off with a simple expression, we create the derivative, which is usually longer. So the input length tends to be uh, longer than the output length. In forward generation, the opposite is true. We since we are starting off by creating the problem, so input length is the one that is smaller here, and then we create the output by passing it through a mathematical framework, which tends to create longer sequences. In integration by parts, we were able to mitigate this problem somewhat, since we generated the output using multiple expressions. So the length of outputs were kind of longer, and their derivatives was easier to find, and they were shorter than what the output was. Uh, yeah, so they generated 20 million examples for forward generation, for 40 million for backward generation, and 20 million for integration by parts there, and 40 each for ordinary differential equations of first and second order each. These are the statistics for the data that has been used. You can see here that they used 11 leaf nodes, that is a single x variable and constants ranging from -5 to 5, uh, except for 0. And they used 4 binary operators: addition, subtraction, multiplication, and division, and 15 unary operators. Like most of these seem to be uh, like sign cost and stuff like that. Uh, so now, since we are over the data set creation, we'll move on to what the experiments were conducted and the results. So the experiment part is like pretty much very simple and straightforward. There is nothing complex here. The trained a model is the trained a sequence to sequence model. If for those who don't know what a sequence to sequence model is, it simply takes a sequence of tokens as input and outputs another sequence of tokens. It is can find its application in mostly in translation, where we'll need to translate a particular sentence in one language to another language. So uh, the sequence to sequence model was used. The architecture that they chose to use here was transformer. The transformer consisted of 6 layers, 8 attention heads per layer, and a dimensionality of 512. So I'm guessing, I mean, the length of the maximum length of possible expression would be 512, because after that it would just get divided up, right? And they used an Adam optimizer and a learning rate of 1e minus 3. The batch size that they used was 256. Now, as I said before, that they removed expression that had more than 512 tokens, since the expression would be split up into multiple uh, inputs, and that wouldn't really make sense. So this is what transformer model looks like. You can see that there are stacks of encoders and stacks of decoders. Each of these encoders consists of multiple attention heads. Now, so these attention heads, the input is passed through each of these individual attention heads. Then the transformer does its magic and calculates the output. Then the output is passed on to the encoder, next encoder, and so on until we reach the final encoder, after which then it is passed on to the decoders to generate the output. So here you can see the transformer converts a French sentence to an English sentence. So it is kind of similar to what our problem is. We're converting uh, problem to solution, but it is basically a sequence. So yeah, so after to decode the sequence that is produced by the transformer, the authors used beam search decoding. So what beam search decoding does is, like for a particular input, the model wouldn't really create a particular output, right? It will create one token at a time. It will generate one token at a time, and like it actually doesn't really generate one token at a time. It gives probabilities for all the possible tokens that will be generated. So we usually take the highest the token with the highest probability, and then the model will produce the next token and so on. So when we do this, it is what we call greedy decoding, where we only take the uh, solution with the best possible results from the start. Like we don't do a search, because if we just go with the highest likelihood, we might end up with a result that is not really the best result, since we are only choosing that. For example, if we had gone with C here, maybe the result would have been a much better result with a higher log likelihood. But if we went with A, we would never be able to, see if it was the best result or not. So to address this issue, there have been multiple techniques that have been used in the past. Like the straightforward answer would be exhaustive search, where we'll look up into every possible path that exists in generating sequence, and we'll just get whichever is the one with the best log likelihood scores. But since that is not really possible, what we do is we used beam search. So we'll take the top 10 tokens that have the best log likelihood scores, and for each of these tokens we'll calculate the next possible token, and among those we'll take the best 10. So for example, we choose A, B, C, D, E here. So among sorry among A, B, C, D here, for example, we have a beam width of 2, right? So we'll only choose two tokens, A and C, and we will calculate what the next token should be. So for A, there will be like with similar tokens, we'll calculate the log likelihood of the next tokens. And for A, I guess B would be the one with the highest log likelihood score, and for C, E would be the one with the highest log likelihood score. Now, it might be possible that both B and C are situated here. So like C would stop here, and that would be the end of it. But if not, then we'll just go on to calculate for each time step, like a time step is for all the possible tokens in a layer, what the next possible tokens are. So we will continue calculating it until we reach the end of the sequence. If you want to look it up more, you can simply search it on Google. It is available. Like the beam search has been used extensively everywhere. So yeah, so the authors decided to go for beam search since by creating multiple hypotheses, if we use a width of 10, we are generating almost 10 hypotheses for each input expression, right? So the authors will have 10 solutions to compare against, and it will give them a like better idea of how their model fares. They also tested for width of 1 and 50 as well. So yeah, to evaluate sequence to sequence models, we generally use blue score, but here we simply calculate the accuracy since like blue score is not really relevant here. Blue score is more relevant in natural language, where there is, I mean, we can't really calculate by accuracy since there are multiple possible forms of a single sentence. But here we can just calculate the accuracy, and if there is any other possible uh, form of the expression, we just calculates it equivalent, or just substitute it in the problem statement, and we should obtain the value of 0 or something like that. So I mean, we don't really need blue here, we just calculate simple accuracy. So these are the results that we are able to obtain. You can see that for integration, in case of forward, even backward generated, and IBP, the accuracy is very high. I mean, we are achieving results close to 100%, right? So for beam size of 1, there is 94, 99, and 96%. And for 10 and 50, it's I mean, it's almost 100%. So I mean, they somehow these models did extremely well when it came to calculating integration, and even in in solving ordinary differential equation. Although beam size 1 kind of did not fare well here, but with the beam width of 10 and 50, they were able to obtain solve ordinary differential equation of order 1 with up to 90 and 95% accuracy. And here also they were able to obtain something close to 80% of accuracy. Now, I mean, these results were much more better than the ones of existing frameworks. You can see here that how they compare against the existing frameworks that are currently being used. So Mathematica is okay, so first of all, we don't compare the data against forward generated data sets, since this was generated using a symbolic framework, and they will always get 100% accuracy for this. But except for that, you can see here that for backward generated cases, Mathematica obtained accuracy of 84%. Like for Mathematica didn't really like stop. They used to time out for after a certain time, so they gave a limit of 30 seconds to Mathematica, so that if the solution is not generated within 30 seconds, they would just assume that it is not able to solve the problem. And MATLAB did pretty bad here, where they were only able to solve 65% of the problem, and Maple around 67% of the problem. But all three of our like of the models that the authors used were able to obtain almost 100% accuracy. Now this is kind of very interesting, since the problem we are dealing with here is symbolic reasoning. The framework, mathematical frameworks that were created to solve these problems, I mean, they were specifically created to solve these problems with hundreds of pages of algorithms, right? So they should be able to get a much more better result here. But instead, we can see that a simple sequence to sequence model that was trained using generated data is faring much better than what they did. Similarly, in the case of ordinary differential equations, you can see that I don't think MATLAB and Maple were able to solve this. So Mathematica was the only one that was used to compare against these kind of problems. So even in that, for first order, all three of the models used by the authors do much better than what the results of Mathematica were. And for second order as well, except for the beam size of one, the other two models do pretty much very well in that case too. An interesting property of the model created by our authors is that we know that like we are using a beam size of around 10, right? 10 or 50. So in a particular time step, the authors are able to obtain around 10 solutions or 50 solutions at a time. So they don't discard everything and just take the one with highest probability. They keep all of these expressions and just evaluate it against the problem. Since it is really easy to evaluate, it doesn't take much time, and they can verify whether it is correct or not. So why not just verify against all 10 of these hypotheses instead of one. So when they do it, they found that although they get a correct result in most cases, they also find that the hypotheses that are the multiple hypotheses that is generated by the model are equivalent to each other. So we would think that for some of these hypotheses, they would be very random and not be relevant to the data at all, since they are not really faring well when it comes to log likelihood scores. But in this particular example here, all of these expressions are equivalent to each other. So all of the solutions are actually correct. So they were able to see that their model was able to generate equivalent solutions without any special training needed to do so. They also looked into the generalization across generators. So they used three kinds of generators: forward generator, backward generator, and integration by parts. So if they used only to train the model, if they only use the forward data, this so that the model will obviously perform better when it came to forward generated validation set. But it did much worse in backward generated data set, because we know that forward and backward generated data have a very stark difference in that in forward generated data, the problem is simpler than the solution, and in backward generated data, the solution is simpler than the problem. So the length of sequences used to differ. So the kind of solution that the model created for while being trained on each of these kind of data also used to differ. So you can see that if you train the model on forward generated data, the accuracy here is very low, and in case of backward generated data, the accuracy in case of forward is very low. Now authors also tested by combining all of this training data together, and you can see after combining this data, the results were much better in every case, in most of these cases. If we combine backwards with IBP, there was a significant improvement in forward generation, forward results, and when combined with everything, all of these results were pretty much pretty great. So yeah, so this was about the generalization across generators, and there is another one, that generalization beyond the generator. Now, for forward generator, we know that we used a mathematical framework to calculate this uh, solutions, to find out the solutions for particular problems. Now, what happened is that SymPy was used to calculate these integrals. SymPy failed to compute many cases in case of where when they try to generate the forward cases, right? They also tested SymPy against the backward data set that they had created, and saw that SymPy only was able to achieve around 30% of 30% accuracy in that case. Now, when the model, since SymPy was used to generate a forward data set, if we train our model on forward data set, it should capture information that is similar to how SymPy calculates results, right? So when our model was trained on the forward generated data set, its accuracy on backward data set was around 17.2. You can see here. So, but an interesting thing happened was that for, even though the data that was used to train our model was the one that was generated by SymPy, model was able to find solutions for problems for which SymPy wasn't able to. So like these are a few problems for which SymPy wasn't able to find the solution, but a forward generated model was able to. So our model was the model of the authors was able to generate beyond the generator that they were used to generate the data. It's kind of confusing. Sorry. Uh, so yeah, I mean, we can see that like for a problem that would be seemingly difficult and that would require rule-based inference, we are able to achieve like state of the art accuracy without needing to do much. So I mean, authors were able to demonstrate that sequence to sequence models can be used for seemingly difficult tasks if the problem is formalized properly. If we can bring together what is needed to be put into the model, we can create like solve tasks that would require rule-based inference. The trained model was easily outperformed state-of-the-art mathematical frameworks that are being used right now. Uh, the results are kind of surprising here because, you know, as I said at the start, neural networks have had difficulty computing simple arithmetic operations like addition and multiplication, but they had no problem when it came to solving these complex tasks like solving integration and differentiation. One of the reasons that the results were good was because we used multiple beam hypotheses. Now, since there was a wide range of hypotheses to choose from, our model always would always perform well if one of these hypotheses even failed. But we can see that even in the case of beam size 1, our model was doing pretty well. So that cannot be the sole reason for the good results. So given these results, the study suggests that future mathematical frameworks might benefit from integrating these neural network components uh, into their environment, because you can see that pattern recognition is very important when it comes to tasks like integration and differential equations. So yeah, I mean, that's it for the paper. Thank you for listening in. If you have any questions, please do ask them.